Okay, so today we're going to look at aldehydes and ketones, which is part of A2 chemistry and carbonyl compounds. So what we're going to look at is what a carbonyl group is, which is just a bit of recap because we have looked at these slightly before, understand how we would represent an aldehyde and ketone, be able to name aldehydes and ketones, and then understand the properties of aldehydes and ketones. So as you know from the past, aldehydes and ketones both contain a carbonyl group, and that is a carbon that's double bonded to an oxygen, and that's the functional group found in compounds that such as aldehydes, ketones, and carboxylic acids. So this is what it can look like. In aldehydes, we always find the carbonyl group at the end of the carbon chain, so it has at least one hydrogen attached to it, whereas in ketones, a carbonyl group is always in the middle of a carbon chain, and so it has two alkyl groups attached to it. And so that is the key difference between aldehyde and ketone, just that positioning of the carbonyl group. Aldehyde at the end of the carbon chain, and in ketones in the middle. So when we're representing aldehydes and ketones, we can't distinguish them by their molecular formula because they have exactly the same functional groups. So for example, we've got an aldehyde and a ketone here. If we wrote out the molecular formula, both have a molecular formula of C3H6O. So if you're just given the molecular formula, you can't actually tell if something is an aldehyde or if it's a ketone. So we have to use the display formula in these situations. So that's really important to note, but just by giving the molecular formula, you will not be able to identify if a molecule is an aldehyde or a ketone. So because of that, when we're representing aldehydes and ketones, we either use the displayed or the structural formula for them. So this is how we would then write them out instead, just so that we can use that, so we can tell if it's an aldehyde or a ketone, so we can see where that positioning of the carbonyl group, for example, here in the middle, is. So we'll use the displayed or structural formulas so we can see that they're where that position of that carbonyl group is. So very, very similar to how we talked about things before. When we've got organic compounds, they have a suffix that allows us to know if it's what type of molecule it is. So aldehydes, we name them using the suffix -al and follows the exact same conventions as when we name alkanes. So for example, this is ethanal, F because we've got two carbons, al because it's an aldehyde. Propanal, we've got three carbons, so it's prop, and then al at the end, because again it's an aldehyde. And then this one would be 3-methyl butanol, methyl, because we've got a methyl group attached at the third carbon, and butanol because we've got 1, 2, 3, 4 carbons, and it's al again because the aldehyde, it's an aldehyde, so our carbonyl group is at the end of the molecule. Ketones, we name them with using the suffix -one on the end. So for example, first one is propanone, prop because we've got 3 carbons, and anone, one because it's a ketone. And then we don't need to put any numbers in here because a ketone always has a carbonyl group in the middle of the molecule. And because there's only 3 carbons, it can't be anywhere other than here. It's also quite important to think about, we can't really have a ketone either with less than 3 carbons because the carbonyl group needs to be in the middle. If it's on either terminal end, it would then be an aldehyde. In this situation, we've got hex and 3-one, hex being used because it's got 6 carbons. Counting the carbon chains, 1, 2, 3. Our carbonyl group is in the third carbon, so hexane, 3-one, and one because it's a ketone. Like alkenes, ketones with 4 or more carbon atoms actually display positional isomerism, and that's because our carbonyl group may appear between different carbon atoms. So because of that, in those cases, we use that number before the -one to indicate the first carbon that's involved. Propanone, we don't need to because it has to be in that second one in the middle. Anything 4 or above, and we can have that positional isomerism, so we have to in those situations. So we're going to quickly go through naming some aldehydes and ketones. So if you were given this, first of all, let's look at how many carbons we've got. We've only got one carbon present. Let me pop my... We've only got one carbon present in this situation, so we know it's going to be meth. Lost. So it's going to be meth something, and or meth, and then obviously it's going to be an aldehyde because that carbonyl group's at the end, it's on the terminal end, so it's going to be methanol. Here, let's have a look at how many carbons we've got. In this situation, we've got 1, 2, 3, 4 carbons. We've got 4 carbons. That means it's going to have bute at the beginning. And it is going to be a ketone because that carbonyl group is not in the terminal end, it's in the middle. We don't need to put a number in because whichever way we count, it will always be butane 2O. So we just put butanone. Here we've got 1, 2, 3, 4 carbons, so it's bute again, but this time the carbonyl group is at a terminal end, which means it's an aldehyde, so it's butanal. Here we've got a little bit more complicated, so let's count the longest chain of carbons. We could get 1, 2, 3, or 1, 2, 3. So it will be prop at the beginning, but we've got a methyl group here, and we've also got a carbonyl group here. So whichever way we count, that methyl group is going to be on the second carbon. So let's pop that in first. So we've got 2 methyl prop because we've got 3 carbons, prop, and it's propanal because it's aldehyde because we've got a carbonyl group at the end. And then finally we've got this. So let's have a look at our longest carbon chain. We could get 1, 2, 3, 4, 1, 2, 3, 4. So it's going to be bute. And we always sort of count where this has been number 2, our carbonyl group. So it'd be 1, 2, 3. So our methyl group's coming off our third carbon. So it would be 3 methyl. Oops, spelling methyl wrong. 3 methyl bute because we've got 4 carbons. Unknown. It's a ketone. Now, what have I spelled wrong? 3 methyl bute. Let's go back a second. Why it was shouting at me. Oh, it's changed it for me. I just put a comma in the wrong place. So preparations of aldehydes and ketones from alcohols. So we can make aldehydes and ketones from alcohols, which we have discussed in the past, but we'll do a quick recap again of that now. So aldehydes are prepared by oxidation of primary alcohols. Remembering what primary alcohols are, it's those ones with just one R group attached. So an example of a primary alcohol would be something like propan-1-ol. So that functional group for the alcohol will be off the first carbon. And we prepare them by oxidizing agents such as acidified potassium dichromate. And what we would do in this situation is we're going to heat them up, and as it goes through, it oxidizes, and so we heat it up, it goes through evaporation, it condenses, our aldehyde condenses, and is collected at the bottom. Ketone, these are prepared exactly the same way by the oxidation of secondary alcohols, so for example propan-2-ol, by oxidizing agents again such as acidified potassium dichromate. This situation, this is where we would often do it under reflux. So it will heat up, and then it will go back in and then go up again. And so this one would be under reflux. And then our ketone would form. If you want to recap any of this information, I would suggest you go back and watch our video on alcohols, because we do cover all of this in great detail there. So I'm not going to go through it lots now. And if you're struggling with the synthesis of aldehydes and ketones, I would suggest going back and watching our video on alcohols. So the properties of aldehydes and ketones, the carbonyl group that is present is actually polar. And it's polar because there's greater electronegativity at the oxygen, which is 3.4, than at the carbon, which is 2.6. And because of this, this actually affects the properties of aldehydes and ketones, such as solubility. So if we've got small aldehydes and small ketones, they're actually soluble in water. And that's because of the hydrogen bonding that can occur between the lone pair on our oxygen of the carbonyl group and the hydrogen of water, because obviously we know water is a polar molecule as well. And so because of that, we can actually have hydrogen bonding occurring there. However, as the size increases of our aldehydes and ketones, our solubility actually decreases, and that's because of the interference in hydrogen bondings by the hydrocarbon tails of our aldehydes and ketones. So we've got some shielding going on, so that interference there. So boiling points of aldehydes and ketones. So if we look at their approximate molecular mass, so smaller molecules up to larger molecules, our aldehydes have got a lower boiling point, ketones higher, and alcohol the highest. And these actually increase as the molecules get larger. So as you can see here, propanone 56 degrees, butanone 80 degrees, and pentanthreone 102 degrees. So they increase with their size. But aldehyde always has a lower boiling point than a ketone. But as we get larger, that gap between them differs, gets smaller, and then actually when we get to these larger molecules, there's no difference in their boiling points. They are exactly the same. So the general increase in boiling points from alkanes to aldehydes and ketones and alcohol is actually due to those intermolecular forces between each type of molecule. Again, if you're not sure about intermolecular forces, look back on some of the videos from last year when we first introduced intermolecular forces. So alkanes are only held together by van der Waals forces. So these are some of the weakest forces, and these forces increase with the size and length of the molecules. So the boiling point of alkanes increases as the alkanes get bigger, but they have a lower boiling point than all of them because they're only held together by van der Waals forces. But they do get stronger as the molecule gets bigger, so the boiling point gets higher as the molecules get bigger. And the polar carbonyl groups that we have present in aldehydes and ketones means that as well as having those van der Waals forces, molecules are actually held together by a dipole-dipole interaction, which then needs more energy to be broken, which thus means that it has a higher boiling point. And then alcohols have the highest boiling point out of all of these, and that's because they're held together by van der Waals forces and dipole-dipole interactions. And as well as that, these molecules can actually form hydrogen bonds with each other. And that's because of that slightly positive hydrogen atom that's present in that hydroxyl group. So alkanes only have the one type of forces acting on them, whereas carbonyl groups have that dipole-dipole, and alcohols have van der Waals, dipole-dipole, and hydrogen bonding. So there's more different types of intermolecular forces working, which need to be broken, which means that you have the highest boiling point out of all the molecules. So that is the first little part about aldehydes and ketones, and next we're going to go into a bit more detail about them. Okay, so now what we're going to look at is carbonyl compounds, those aldehydes and ketones in a bit more detail, and we're going to look at the reactions of them. So by this, we mean we're going to be looking at the reactivities of them, the uses and dangers of HCM, the reduction of aldehydes and ketones, and being able to distinguish and detect aldehydes and ketones. So we know that double bonds require a lot more energy to break than single bonds, and compounds with double bonds are generally more reactive as addition reactions are possible. So some of the chemical properties of aldehydes and ketones actually just result from that polar nature of that carbon double bond oxygen bond, that carbonyl group, which we just talked about. And we were saying about the boiling points of them being higher than alkanes, and the fact that the smaller aldehydes and ketones are soluble in water. So that positive charge that we've got on the carbon atom actually makes it open to attack by nucleophiles. And we've looked at nucleophiles before, and we've done nucleophilic addition. And the aldehydes and ketones can actually be reduced. And when we reduce them, we can form primary, secondary alcohols, respectively. So in the past, when we've talked about oxidizing alcohols, primary alcohols and secondary alcohols to make aldehydes and ketones, respectively, this is exactly the same process, but in reverse. So we're just reversing it, we're reducing rather than oxidizing. But as well as being able to reduce aldehydes and ketones to form primary, secondary alcohols, respectively, we can actually also oxidize aldehydes. And when we oxidize aldehydes, we can actually oxidize them to form carboxylic acids. So what we're going to look at now is nucleophilic addition reaction of cyanide. So what we're going to focus on is that positive charge on that carbon atom, and that makes it open to attack by nucleophiles. And it could be a nucleophile such as cyanide, and which can be used to extend the length of that carbon chain. So what happens is we've got a lone pair on the cyanide ion. So here we go, we've got our alcohol, not an alcohol, sorry. We've got our carbonyl group here. And we've got a lone pair on that cyanide ion, on the carbon on it. And that lone pair on the cyanide ion is attracted to that partially positive charge on the carbon atom in our carbonyl. And the electrons in that carbon double bond oxygen are repelled to the electronegative atom. So again, those curly arrows that we've discussed in the past, we've got that attraction of the electrons from the lone pair to that positively charged carbon, and then those electrons in that double bond are then repelled to the electronegative oxygen atom. Then what happens is this then results in the formation of an intermediate, and that intermediate has a lone pair and a negative charge on the oxygen atom. So we get this intermediate being formed, and we've got a lone pair of electrons and a negative charge on that oxygen now, and that's our intermediate. In the second stage of nucleophilic addition, what happens is a hydrogen ion, and that's from the solvent or a molecule of HCl, and that actually comes along and acts as an electrophile. And when it does this, it is attacked by the oxygen atom of the intermediate. And you can see that there because of that lone pair on the oxygen atom. So it's attacked. And that lone pair on the oxygen atom is actually attracted towards that positively charged hydrogen ion, and it forms a covalent bond. And if that cyanide ion that we had at the beginning is a nucleophile, we actually form a hydroxynitrile, and this is what a hydroxynitrile looks like. And that's nucleophilic addition using cyanide. So hydrogen cyanide is a highly volatile liquid, got a boiling point of 26 degrees, and it has a faint bitter almond smell. In solution, hydrogen cyanide partially dissociates. So as we were talking about before, that's why I was saying you have your cyanide ion and the hydrogen ion, and because it dissociates partially when it's in solution. It's highly toxic, and it's highly toxic because it inhibits a mitochondrial enzyme that is needed for respiration. Because it's really volatile and flammable, it's actually really hard for us to handle safely. So if we're ever going through oxidation of any of these molecules or wanting to do nucleophilic addition, rather than using hydrogen cyanide, we sometimes will use potassium cyanide. We use this because it's solid at room temperature, so it's a lot easier for us to handle. And this is an acidified solution, contains both the hydrogen ions and the cyanide ions that are needed. So reduction of aldehydes and ketones. So as we've said, we can reduce these back to alcohols. As such, we can oxidize the alcohols to aldehydes and ketones. And we can do this using reducing agents like sodium tetrahydroborate. And they are a source of the hydrogen ion, which will come in and act as a nucleophile. So to start off with, key point, which you should know by now, aldehydes are reduced to primary alcohols by reducing agents. Primary alcohols are oxidized to aldehydes by oxidizing agents. So what might happen is we've got our aldehyde here, and we've got a lone pair on the hydride ion. So hydride ion is bound. We've obviously got this polar carbonyl group, and a lone pair on the hydride ion is actually attracted to that partially positive charge of the carbonyl carbon. The electrons in the carbon double bond oxygen are repelled to the electronegative oxygen atom, very similar to stuff we've talked about before. When this happens, this results in the formation of an intermediate, and that intermediate has a lone pair and a negative charge on the oxygen atom of the aldehyde. A positive hydrogen ion, which is from a solvent, actually acts as an electrophile and is attacked by the oxygen atom of the intermediate. And that lone pair on the oxygen is attracted towards the positively charged hydrogen ion and forms a covalent bond, and this results in the formation of a primary alcohol. Ketones are reduced to secondary alcohols by reducing agents. As such, secondary alcohols are oxidized by oxidizing agents to form ketones. A similar way, the lone pair on the hydride ion is going to be attracted to that partially positive charge of the carbon on our carbonyl group, and the electrons in that carbon-oxygen double bond are going to be repelled to the electronegative oxygen atom, as we can see here. This will then result in formation of an intermediate with a lone pair and negative charge on the oxygen atom of the ketone. A positive hydrogen ion from the solvent acts as an electrophile and is attacked by the oxygen atom of the intermediate. And then finally, the lone pair on the oxygen is attracted towards the positively charged hydrogen ion and forms a covalent bond, and as such results in the formation of a secondary alcohol. So how do we actually distinguish between aldehydes and ketones if we've got the substance in front of us? So we actually work on the basis that aldehydes, but not ketones, have reducing properties and can therefore be oxidized to carboxylic acids. So again, this is something that we've talked about before, so we'll go through really, really quickly. And it is the silver mirror test. And this is where we use tolerance reagent, which sometimes is called ammoniacal silver nitrate. In this situation, tolerance reagent is made, and we make this by adding a small amount of aqueous sodium hydroxide solution to aqueous silver nitrate. And when we do this, it forms a brown precipitate of silver oxide. Once we've made the tolerance reagent, aqueous ammonia is then added until the precipitate dissolves to form a solution of the silver amine complex. So the test substance, whatever it is then added to our tolerance reagent, and we then warm the test tube in a hot water bath. And so that's really important to do. So we've got a tolerance reagent. I don't know why this is really behind. We're going to add our test substance to it and warm it in a hot water bath. If an aldehyde is present, it reduces the silver amine complex to the metallic silver, and it forms a silver mirror precipitate on the inside of the test tube. So we heat it up in the water bath, and what we're hoping to see is if an aldehyde is present, it will reduce the silver amine and form that metallic silver. And it will form that silver mirror precipitate on the inside of the test tube. If it does that, that means an aldehyde is present. We can also test using Fehling solution, which is what we've talked about before. And Fehling solution is a blue alkaline solution of copper-2 ions. We add Fehling solution to an empty test tube. We don't have to make this one up. We just add this one to a test tube. Once we've added it to the test tube, we add the test substance as well. And then we warm this in a hot water bath. Once it's been warmed in a hot water bath, if an aldehyde is present, the solution will turn a brick red colour. And that's because the aldehyde reduces those copper-2 ions to copper-1 ions, which form a precipitate of copper-1 oxide, which has that brick red colour. So rather than detecting if something's an aldehyde or a ketone, we might actually just want to know if something's got a carbonyl group in it. So if we want to just know if a solution's got the presence of a carbonyl group, we can use Brady's reagent. So if we've got an unknown compound and we want to know if it's got a carbonyl group in it, we can actually react it with Brady's reagent. Brady's reagent is 2,4-dinitrophenylhydrazine, and it will produce a yellow-orange precipitate. The precipitate is a 2,4-dinitrophenylhydrazone derivative. It's impure, so it is separated using filtration, and we use a Buchner funnel and then wash this with distilled water. Remember, Buchner funnel has a vacuum to pump away. This derivative then, so once we've collected this derivative, is dissolved in a hot solvent, so it could be something such as ethanol, and then we cool it so that it recrystallizes. The crystals can then be filtered, washed, and allowed to dry, so now they are pure. So again, go through the Buchner funnel, filter them, then we will wash them, and then we will allow them to dry, and we should now then have pure derivatives. So finally, a sample of these crystals can then be added to a narrow capillary tube and then placed in a melting point apparatus. And so this allows us to measure the melting point of the crystals. Once we know the melting point, we can then find out if it's got a carbonyl group in. So how this apparatus works is it slowly heats the crystals, and these crystals are viewed through a magnifying lens. By looking up the melting point in a database, the aldehyde or ketone in the sample can then be identified. For example, melting point of these crystals is 128 degrees. So you would look up in a database to find out the aldehyde or ketone in the sample. And we're going to end that there and go on to the next little section of aldehydes and ketones. Okay, we're going to quickly look at carboxylic acids. I know we have covered these again in the past, so this will be a quick sort of overview, but we do have to recover it again when we're looking at carbonyl groups. So carboxylic acids, we're going to have a look at what they are, how to name them, and the properties of carboxylic acids. So as you know, carboxylic acids have a carboxyl group, similar to a carbonyl group, but it's a carbon double bonded to an oxygen and then an OH, consisting of a carbonyl group and a hydroxyl group. and these are attached to the terminal carbonyl carbon. Carboxylic acids are always named using the suffix oic acid. Methanoic acid, as you can see here, is the simplest carboxylic acid and is found in bee and ant stings. Ethanoic acid is the acid that gives vinegar its sharp taste and smell. It's also really important in the chemical industry, and about 6.5 million tons are used worldwide each year. So naming carboxylic acids, so for example here, we've got one carbon, so this would be methanoic acid. Here we've got 1, 2, 3, 4 carbons, so this would be butanoic acid. Here we've got 1, 2, 3, 4, 5 carbons, but we've also got a methyl group coming off the second carbon, so it would be 2-methyl. How many carbons did I say it was? 5. 2-methyl pentanoic acid. 2-methyl. Do you want me to put comma in? Occasionally wants commas. So passage by count, if it's written 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Ignore that. It is not 4-methyl hexanoic acid because I cannot get 6 carbons out of that unless I've completely lost my mind. 1, 2, 3, 4, 5. That is 5. So no, that is 2-methyl pentanoic acid. And then here we've got 1, 2, 3, 4, 5, but we've got that chlorine there. So it's 2-chloro. One, 2, 3, 4, 5. Pentanoic acid. Pentanoic acid. Oh, I know it's right. No, it's not 3-methyl pentanoic acid because that's got a chloro group in it. These answers are wrong. What I put is right. So sorry about that. So boiling points of carboxylic acids. We're just going to have a look at what happens with their boiling points. So, we're going to compare them to alkanes, aldehydes, alcohols, and carboxylic acids. So, not helpful. As you can see, or you could see, but it's now disappeared, so hopefully it will reappear. There we go. Carboxylic acids have a higher boiling point than alkanes, aldehydes, and alcohols, and these increase with the molecular size of a molecule. The boiling points are higher than those of compounds of similar molecular mass, and that's due to that hydrogen bonding between the molecules. So it's going to have those van der Waals forces, it's going to have those dipole-dipole interactions, but it's also going to have that hydrogen bonding. So how might we synthesize carboxylic acids? Well, we use those harsher conditions when preparing aldehyde. So again, this is a quick recap. If you want more information and more detailed process of how we synthesize carboxylic acids, then I would suggest going back and watching the alcohols video. So as you know, to make a carboxylic acid, we have a primary alcohol and we mix it with an excess, and that word excess is really important, of acidified potassium dichromate. And what this does is it ensures there's enough oxidizing agent present for the complete oxidation of the alcohol. So it needs to be complete oxidation, so we need it to be in excess. We also add sulfuric acid to the flask. So we have that acidified potassium dichromate and sulfuric acid. And the ethanol, because obviously we need that primary alcohol as well. So then the reaction mixture has to be heated for longer than if we were just forming aldehyde. So we heat it, and this reaction is then going to be refluxed. And when we reflux something, this involves us fitting a condenser and we heat the mixture. As our mixture is going to be boiling, the aldehyde will evaporate and then it condenses repeatedly and drips back into the reaction mixture, which allows it to then continue to be oxidized. And what you should notice is the color changes in the reaction mixture from being orange to green. And obviously we've got that condensation tube going on. So the solution changes color, and that color change is due to a change in oxidation states of the chromium ion. It goes from being a +6 in the dichromate ion to a +3 in the final mixture. So carboxylic acids can be created by the oxidation of aldehydes by using oxidizing agents such as potassium dichromate. But we can also create them by the oxidation of primary alcohols, again using potassium dichromate. So we can do it either way. So we can either oxidize aldehydes to make carboxylic acids, or we can oxidize primary alcohols under reflux with potassium dichromate to form a carboxylic acid. Carboxylic acids can also be prepared by the hydrolysis of nitriles. What we do in this situation is we go through reflux again, but the nitriles reflux with water and hydrochloric acid, and the carboxylic acid can then be distilled from the reaction mixture. We're just going to then go on to the final section of carbonyl groups. And this is our final section of carbonyl compounds, and this is the reactions of carboxylic acids. So we're going to look at the reactivity of carboxylic acids, understand how to form a carboxylate ion, and understand reactions with carbonates and alkalis. So the reactivity of carboxylic acids results in part from the polarization of its bonds. So as we can see here, we've got a polarization on the carbonyl group that we've talked about before, but we've also got that polarization on that hydroxyl group. So the reactions of carboxylic acids include neutralization. Our carboxylic acids can actually lose a proton to form a carboxylate salt. It can go through nucleophilic substitution, and that positively charged carbon that we can see here is attacked by a nucleophile, and it results in substitution of the OH group. Or it can go through esterification, and this is reaction with an alcohol to form an ester. So if we were to form a carboxylate ion from a carboxylic acid, this can happen because these carboxylic acids are weak acids, and they actually partially dissociate in aqueous solutions. So here we've got our carboxylic acid and our carboxylate ion. And what happens is that negative charge is delocalized across the carboxylate group, and it results in a more stable ion. The delocalization is represented by adding a second dotted line that you can see here between the two oxygen to the carbon-oxygen bonds, and which are both equivalent to each other. So that is how we could represent that. Carboxylic acids are the only organic compounds that are actually strong enough acids to react with either sodium carbonate or sodium hydrocarbonate. So the reaction of ethanoic acid and sodium carbonate you can see here, and it forms sodium ethanoate. If you reacted methanoic acid and sodium hydrogen carbonate, you would form sodium methanoate. So the formation of bubbles of carbon dioxide gas make these reactions really useful as a test for carboxylic acids. If we were to react a carboxylic acid with alkalis, such as sodium hydroxide, we form a neutralization reaction. So if we had propanoic acid and sodium hydroxide, we would form sodium propanoate and water. And if we reacted butanoic acid and potassium hydroxide together, we'd form potassium butanoate and water. So that is the end of this topic of carbonyl groups.